Okay, so we've got the light source, light spreading out, it hits the wall, it only gets through with these two slits. So we can treat those two slits as the new sources. If we're considering a point on the other wall that's exactly halfway in between, or exactly across from the halfway in between point, we can trace out the rays, the path that light is taking from the top slit to this location and from the bottom slit to this location. And what do you notice about those two paths? Is there any difference between those?
They're equal?
Yeah, they're equal distances. So at the center, delta x equals 0. You have the same path length. So if we were to write out an actual phase chart there, if we do our usual 2 pi times t times delta frequency minus 2 pi times delta x over wavelength plus delta phase shift equals delta total phase. In the center, we have, they arrive at the same time, they have the same frequency because they come from the same source. So this term is going to be 0, no difference in time times frequency. Is there any difference in wavelength or distance traveled? They're traveling the same distance, right?
No.
Complete symmetry here. And also they're the same wavelength. How do we know they're the same wavelength?
Yeah, the source is the same.
Yeah, these two waves are ultimately coming from the same source. Even though the split up from these slits means we're essentially treating each slit as a separate source, they originally came from the same source, so we can treat them as automatically have the same wavelength. And at this central location, both of the paths are the same distance, so we got no difference in this term. Do we have any difference in phase shift?
No.
And how do we know there's no difference there?
Because they came out of the same source?
Yeah, once again, they came from the same source. There's no reason to expect this ray of light and this ray of light to behave differently in terms of phase. So we got no difference in phase shift. Add those together, we get 0 as the total phase difference. And 0 means what type of interference?
Constructive.
Yeah, so we should expect constructive interference at the center, meaning what you would see is a very bright spot here. And again, we call that the central maximum. Maximum in the sense of maximum brightness, central because it's in the center of the pattern. Can you re-explain why they're both equal to 0? Yeah, for this one, there's never really going to be any difference in time because both waves arrive at this location at the same time. The only time you get a delta frequency is if the waves were from two different sources with different frequencies. For instance, 2 waves of light with different colors or 2 sounds with different pitches. But since they're both from the same source, they're guaranteed to have the same frequency. So there's no difference. For this one, we can assume there's no wavelength difference, again, because they came from the same source. And in this particular case, there's no path difference. They both travel the same distance because we've got complete mirror image symmetry here. Both of the paths are the same length. So no difference there. And also no phase shift difference because, again, they're from the same source. Those all add up to 0 as the total phase difference, and no difference in total phase guarantees constructive interference. Any other questions on that so far? So we know the center is going to be constructive, at least if we can assume all these are true. Let's take a look at another location. Let's say we go some distance upwards on the wall. And let's say we are now looking at this location as our point of interest. And the way we're going to label this, you could label this point by measuring a distance. And that distance we're typically going to call y, in the sense that it is a vertical distance along this far wall. But it turns out the distance doesn't really matter as much as the angle does. If you think of the line of sight from the center, that is this point directly between the two slits, angle up to the line of sight. That angle turns out to be a much more useful way of labeling this point. If you remember the patterns of constructive interference we get, those patterns were along a certain line. If you were to move this wall backwards, the pattern of bright and dark spots would spread out as you move it backwards. The angle is really what's important, not the height. So let's label that angle theta. So theta represents the angle of elevation of the line of sight to the point of interest on the wall. And our reference point for that is going to be the central maximum, the center of the pattern. So that point directly across from the center of the slits, we're going to call that theta equals 0. And then all the other angles are going to be measured from there. Positive angles above, negative angles below. And so ideally, we want to be able to write some formula for interference in terms of theta. Other distances that might be involved, the distance between the wall with the slits and the other wall is usually called sometimes capital L or sometimes capital D, depending on what variables they want to use. But I've seen either one of those. And the distance between the slits is usually called lowercase d.
Casey?
Yeah.
I got a little lost. Why is that our point of interest? Like, was there a reason for it?
No specific location, just a point on the wall. Because we already know we get constructive interference at the exact center.
Mm-hmm.
We want to know what happens if we choose some other point.
Okay.
So this isn't really one specific location. It's just a location we want to analyze.
Got it.
I'm
Thanks.
saying, suppose you have some other location on the wall, some distance y above the constructive or the central maximum, and that also translates to some angle theta. And it's going to turn out that it's more useful to look at it in terms of the angle. What does the value d represent? The lowercase d here is the distance between slits. And then the capital D or capital L is the distance from the slits to the screen that we're projecting onto, the far wall. And one of the assumptions we're going to be making here, we're going to assume that the slits are very close together. In a typical experiment, the distance between slits is going to be maybe a millimeter or two. And the distance from wall to wall is probably going to be several meters. So we're assuming that this horizontal distance is probably like thousands of times longer than this tiny distance between slits. Usually we use experiments like this to analyze what's going on with slits that are very close together, like too close to measure with a ruler. So we've got microscopic distances between slits and longer distances from wall to wall. That's one of the assumptions we're going to be making here. And as far as the geometry is concerned, if we take a look at the actual distances, we've got one ray of light going from the top slit to this location of interest. So let's call that distance x1. And another ray of light going from the bottom slit to this same point of interest. We'll call that distance x2. Are those the same length?
No.
These are definitely not the same length, right? We no longer have that mirror image symmetry. It looks like x1 is traveling a slightly shorter distance, x2 is traveling a slightly longer distance. So we now have a delta x. There's still no difference in lambda though, so we can factor lambda out of the delta here. So we could write this as 2 pi over lambda times delta x, the difference in path length. We still have no difference in time because they arrive at the location at the same time. We still have no difference in frequency because they come from the same source, so this is still 0. Again, they're still from the same source, so there's no phase difference. But there now is a path length difference. 2 pi over lambda times. And let's figure out that path length difference. If we write that as x2 minus x1, or x1 minus x2, the order doesn't really matter here. In fact, what's the only difference order of subtraction is going to make? Like if you subtract 8 minus 5 versus 5 minus 8, what's the only difference in the results?
The sign.
Yeah, you just get a difference in sign. And we have a negative sign here formally, but whether this results in positive or negative ultimately just depends on which order we're subtracting. If you've got multiple terms, you need to be careful you're subtracting in the same order each time for consistency. But if you've just got one term, you can subtract in any order you like. So let's just assume we're subtracting in the order that's going to make this a positive result, just for simplicity. So we've got x2 minus x1, let's say the longer distance minus the shorter distance. And we want to figure out what is that delta x? What's that extra distance traveled? And a useful way to look at that geometrically is if you take the distance traveled by x1, so you got this distance here, if you imagine swiveling that across and cutting it off from x2, so let's say we just make another copy of x1. x1 is a little bit shorter, so we have some leftovers here. The leftovers is the extra distance traveled. That's our delta x. We've got some distance that's the same, and it might help to imagine here that you're backtracking from the destination. Reverse backtrack from the destination, same distance x1, but x2 has a little bit of extra distance. That little bit of extra distance is the delta x that we're talking about in the phase chart. So that little bit of extra distance is what determines the type of interference. Everything else, the rest of the long distance is identical. The little bit of extra distance is what matters here. Any questions on that so far? So let's see if we can use some geometry to find that little bit of extra distance. I'm going to zoom in on this region right here, because this little region right in the corner is where the magic happens. This is what's causing the different types of interference. So if we take a closer look at that little triangle, so we've got the slits. We've got D, the distance between the slits. We've got one of the rays traveling outwards here. And what we care most about is that delta x. So we've got one ray traveling out like this, one ray traveling out like this. Are these rays of light parallel, by the way? Like ray 1 and ray 2, would you describe those as parallel?
No.
No, because the definition of parallel is that they never meet, right? These rays of light definitely meet at some point. But since they're meeting a long ways away, we can treat them as almost parallel. If you look at these really close up, you might think these are almost parallel. They are pretty close to parallel. They are going to meet, but it's a long way off. So for purposes of the zoom in, we can treat these as effectively parallel. If we drop this perpendicular here, if we cut off distance x1 from x2 to see what's left over, and mark the delta x. So this is the actual extra distance traveled. So this is the distance we actually want to find. We want to know what's the extra distance traveled by wave 2, since that's going a little bit further. And do we know any angles here?
Are the right angles? Or...
Yeah, we know we have some right angles. So this angle, and this angle are all right angles. And we know also, what were we using the angle theta to represent? That angle theta in our original setup that I'd kind of drawn over. Theta was this angle of elevation from the slits upwards, well, from a horizontal at the slits upwards to the actual line of sight to the point of interest. So if we draw that in here, there's theta, the angle between the horizontal and the line of sight. If this is theta, what would this angle have to be?
90.
Well, these two together make 90, right? If we've already used up theta, what's left?
Oh. 90 minus theta.
Yeah, this angle is going to be 90 minus theta. If we then take a look at a different pair, we've got a horizontal and a vertical. So these form a right angle. If this is 90 minus theta, how much is left for this angle? We've got 90 minus theta plus how much more would equal 90?
Theta?
Yeah, so this is just another copy of theta. Because theta plus 90 minus theta makes a right angle. So in this triangle, we now have a right triangle where one of the angles is theta. Theta in the sense that it's the same angle as the angle of elevation. And if we know, like let's say we know the distance between slits already. If you know the distance in between slits and you know this angle theta, how would you calculate delta x? What trigonometric ratio would be useful there?
Sine.
Yeah, we could say sine of the angle, sine of theta, equals opposite over hypotenuse. That'd be delta x over d. And then if you solve that for delta x, what would you get?
D times sine of theta.
There we go, d times sine of theta. So this is really the key to the double slit experiment. This idea that the path length difference, the extra little distance traveled by the longer path, that extra little distance is the distance between slits times the sine of the angle of elevation. So if you know the angle of elevation to the location of interest, you can take the sine of that angle, multiplied by the distance between slits, and that tells you the extra distance traveled. And that is the delta x that's going to be in our phase difference, our phase equation. So we can replace delta x with d sine theta. Any questions on that so far? And let's say we're specifically looking for a bright spot. If we want constructive interference, what would we expect delta total phase to equal?
A whole, like, integer that's even.
Yeah, 2 pi times n. 2 pi n, because that 2 pi is a full cycle, 2 pi times n would be a whole number of full cycles. So if we're specifically looking for constructive interference, a bright spot in this pattern, we should assume that the total phase difference equals 2 pi n. So let's try applying that. If we just set total phase difference equal to 2 pi n, and in this case, the total phase difference is just the position term, then we're going to get two pi over lambda times the path length difference, d sine theta, equals 2 pi n. And we can simplify this further as well. What can we get rid of here?
2 pi.
Yeah, we've got a 2 pi on both sides. So if we just divide both sides by 2 pi, the 2 pi's will cancel out. And also, how could we get rid of this lambda?
Multiplying it over?
Yeah, if we just multiply both sides by lambda, we get d sine theta equals n times lambda. Because the d sine theta is the extra distance traveled. So this is really just saying if the extra distance traveled is a whole number of wavelengths, that is a whole number of cycles worth of distance, then we get constructive interference. We get bright spots under these conditions. Anytime d sine theta equals a whole number times the wavelength, that angle results in a bright spot on the wall. So we can use this to predict where bright spots appear. If you plug in 0 for n, you just get sine theta equals 0, so theta is going to be 0. What would it mean if theta is 0? Where is that on the wall?
Directly like across from it?
Yeah, we were using this central bright spot as the reference point for our angle. So 0 degrees means straight across. So when n is 0, you get the angle is 0, and that corresponds to the central bright spot. If you then plug in n equals 1, you could solve for theta, and that would tell you the first bright spot above the center. Plug in n equals 2, you could solve for another angle and find the second bright spot above the center. So you could think of n, I mean, mathematically, n just has to represent a whole number, any integer. But conceptually, you could think of n as representing which bright spot you're talking about. N equals 0 means the central bright spot. N equals 7 would mean the seventh bright spot above the center. N equals -3 would mean the third bright spot below the center. N is just keeping count of how many bright spots we've passed so far, or which bright spot we're dealing with. But this equation should give you the angular location of any bright spot you want. And that is, of course, assuming you know d and lambda. But this can go in other directions as well, because if you're actually just shining a light on some slits, you can look at the bright spots and measure where they are. So you can measure the angle to, let's say, the 10th bright spot. The first bright spot might be difficult because maybe they're so close together it's difficult to measure the angle. But let's say you count out to the 10th bright spot and measure that angle. So you'd say n is 10, theta is whatever angle you measure, and lambda, what does the wavelength of a light represent? Like if you know the wavelength of a wave of light, what do you see about that?
Color.
That's the color. So if you know exactly what color your light source is, maybe you're using a laser that is known to emit exactly 700 nanometer wavelength. So maybe you know the wavelength, you can count the 10th bright spot, or whatever bright spot is easy to measure, and you can measure that angle. In that case, what's the only unknown left in the equation?
D.
Yeah, the distance between slits, d. So this can actually be used as an experiment to measure the distance between slits. And this is very useful because in many applications, maybe you've got a sheet of metal with 2 tiny pinpricks in it that are so close together that there's no ruler that would be fine enough to measure them. So you can't measure the distance directly with a ruler because they're too close. But you can certainly shine light on that metal. You can measure the angle of the resulting interference pattern, and maybe you know the wavelength of the light. Plug in those values, solve for d, and you now know the distance between the slits with a great degree of precision. Or alternatively, if you already know the distance between slits, maybe you could shine some unknown mystery light on these slits, plug in the value of D, measure the angle of the whatever bright spot you want to count to, and then solve for lambda. So you can use this experiment to find the wavelength of a new light that you don't already know the wavelength of. Any questions on that so far?
So yeah, when you're saying to measure the angle, do you mean the angle from the slit, like on the drawing on the right, or do you mean like that central angle that you drew on the drawing of the left?
They turn out to be the same. If you draw the angle between, so you've got a horizontal and you've got your line of sight to the point you care about.
Mm-hmm.
That angle of elevation turns out to be the same as this angle in the triangle. So that's why we can use that angle in the first place. But this angle would presumably be more practical to measure. Because if you just mark this bright spot and this bright spot, if you were to, maybe you stretch out some string along those lines of sight, and you can measure that angle with a protractor.
Okay.
Casey, I had a quick question.
Mm-hmm.
So like, like on an exam or a quiz, would they give us like what the angle is, or do we have to figure it out? I'm still kind of confused. Like,
it really depends on the circumstances. As long as you've got an equation like this, as long as you have any three of those values, you can immediately solve for the third or the fourth value.
Mm-hmm.
Or maybe you've got the wavelength and the distance. You could plug in various whole numbers for n and get various angles for theta. So those would be the various angles where bright spots would appear.
Okay, so they would probably give us at least like 3 out of the 4, like.
I would expect something like that, yeah. Or maybe they give you 2, and then you would plug in several values for n to find several angles where bright spots appear.
Oh, okay. Okay, thank you.
What was that?
Oh, thank you.
Another variation on this, we've been assuming we're looking for bright spots. What if we had wanted dark spots instead? If we wanted destructive interference, what would we do differently? We know bright spots appear at a whole number of cycles. Destructive interference would be what instead?
The odd number.
You could think of it as an odd multiple of pi. I think it might be more practical in this case to instead think of it as something and a half cycles. So for bright spots, we would want 2 pi n. For dark spots, destructive interference, I would write that perhaps as 2 pi times n plus 1/2. That's something and a half cycles, where again, we're assuming n is an integer, a whole number. And even if you multiply that out, the 2 times n and 2 times 1/2 would become pi times 2n plus 1, which is still pi times an odd number. So if we do exactly the same arithmetic or exactly the same algebra, we're going to get the same result, except instead of n, we're going to have n plus 1/2. So we find dark spots when d sine theta equals something and a half times wavelength. And those end up being between all of the bright spots. For instance, when d sine theta equals 1 lambda, or d sine theta equals 2 lambda, or d sine theta equals 3 lambda, those are all going to be bright spots. But if d sine theta equals 1/2 lambda, or if d sine theta equals 1.5 lambda, or 2.5 lambda, or 3.5 lambda, those are going to be the dark spots between the pairs of bright spots. Any questions on that so far?
Casey, could you just explain one more time what n like means here in like this situation?
Yeah, for this equation, I think of n as representing a count of which bright spot we're talking about. So at the very center, the central maximum is going to be n equals 0. And then the next bright spot, the first bright spot beyond that is going to be n equals 1. The next bright spot is going to be n equals 2. The next bright spot is going to be n equals 3, and so on. So
okay.
N is counting up which bright spot we're looking at.
And that's the same also for the dark spots, but just counting up from, okay, that makes sense.
Mostly, although if you want to think of the dark spots like that, I would write this as n minus 1/2 instead of n plus 1/2. Because the first bright spot is going to appear at 1, or the first dark spot would appear at 1/2 times lambda. So if you want to think of n as representing the count of how many bright or dark spots, the first dark spot would be at 1 minus 1/2 lambda. In other words, 1/2 lambda.
Okay, and then the other way you wrote it, it would just be like 1/2, like above a bright spot. Is that what you're saying?
Yeah, so like if you plug in 1 for n, you get 1.5. That would mean the dark spot just beyond the first bright spot.
Okay, okay, that makes
sense. It's just going to be something and a half times lambda to get a dark spot.
Okay, okay, thank you.
One other useful thing we can do with geometry here, we've been looking at this in terms of describing each position as an angle, but angle can be kind of inconvenient. You don't want to have to stop the experiment and stretch out strings from here to here and here to here and hold up a protractor to measure the angle. Instead of measuring the angles, what's usually a lot easier to measure than angles? Like if you've got a triangle and you'd rather not have to measure the angle, maybe you don't have a protractor or something, what else about that triangle could you measure more easily?
The length of the sides.
Yeah, the lengths are much easier to measure than the angles. You just hold up a ruler or stretch out a tape measure, or even just stretch out a string and then take the string somewhere else to measure it on a ruler. So distances are usually much easier to measure than angles, and with much more precision also. So ideally, we want to be able to rewrite this in terms of distances instead of in terms of angles. So if we take a closer look at this angle, we've got this length, and this length form a right triangle. And we're already calling this angle of elevation theta. And we even have some of these side lengths labeled. We've got this distance from wall to wall is called L or D, depending on which variable you want to use. This vertical side is called Y, the height from center up to the bright spot or dark spot we're talking about. And let's call this distance H for hypotenuse. We could now use some right triangle trigonometry on this triangle. And since we have a sine theta in our formula here, let's go ahead and find sine theta in this triangle. In this triangle, how would you write out sine theta?
Y over hypotenuse?
Yeah, that opposite side y divided by the hypotenuse h. So we could rewrite this equation just replacing sine theta with y over h. And that replaces the angle with distances. So we'd be able to write out the whole thing in terms of distances. The only disadvantage there is that h is going to be difficult to measure. You'd have to, like if you're looking at different bright spots, you'd have to measure the hypotenuse differently every single time. And that's inconvenient. But one thing we can use here is the fact that we're usually looking at very small angles. If the angle we're looking at is very small, if we're looking at a bright spot very close to the center, a small angle. If the angle is very small, what would you expect about the length h? Length h is going to be very similar to what other length?
L or D.
Yeah, that's going to be very close to that other side length L. So we can say if theta is small, that is, if the point of interest, if the bright spot we're looking at is very close to the center, then we can say that instead sine theta is approximately y over capital D instead. And one of the advantages there is that if we look at different angles, h changes a little bit, but D doesn't change. So if we just use D instead as an approximation, we don't have to worry about changes. We can just replace sine theta with y over D. And then we get bright spots when d times y over d. We can replace sine theta with y over d equals n times lambda. And this is going to often be much more convenient because we don't need to worry about angles at all. We can just say distance between slits times height up the wall divided by distance from wall to wall equals a whole number of wavelengths if we're looking for a bright spot. That rewrites it entirely in terms of distances, so we don't have to worry about angles at all. And this can be useful if, for instance, you're trying to solve for a distance up the wall. You don't need to worry about angles at all. You can just use this formula and solve for distance on the wall. So either of those work. This one's exact. This one's an approximation, but it's a pretty close approximation for points very close to the center. Any other questions on that?
How close to the center do you have to be before you can use that?
It really depends on how accurate you want to be. If you're just looking for a reasonable approximation, you can spread out pretty far and still be pretty accurate. But I think it's a problem would presumably tell you we're assuming a small angle, or assuming you're looking at points close to the center. If you're going really far out, like, I don't know, 80 degrees or something, this is going to be a terrible approximation. If you're within like a couple of degrees, it's a very close approximation. Between those, it really depends on how accurate you want to be. What you might want to try for a few examples anyway is try both formulas and see how the results compare. They should be pretty close as long as the angle's not too big. Any other questions on that?
So is that what? Oh, sorry. So is that why sometimes they say sine of theta is like approximate to tan of theta?
Yeah, exactly. In fact, tangent of theta would be exactly opposite over adjacent. Sine of theta is opposite over hypotenuse. But as long as the angle is very small, the adjacent side and the hypotenuse are almost the same length anyway. So sine theta and tangent theta are almost the same if the angle is small enough.
Okay, so if they say that, could we use like the d times y over d equals n times wavelength equation?
Exactly.
Like
in fact, the y over d is sine theta. Y over d is actually tangent of theta. But again, if theta is small enough, sine of theta is about the same as tangent of theta.
Okay, thank you.
In fact, we can actually take that approximation one step further. Sine theta, as long as theta is small, sine theta is approximately equal to tangent of theta. And they're both approximately equal to theta itself as long as theta is measured in radians. If it's in degrees, that last bit doesn't hold true. But in radians, sine, tangent, and the angle itself are all almost the same value. And you can see that on a graph. If you graph y equals x, y equals sine x, and y equals tan x in radian mode, close to the origin, they're all going to be pretty close to the same curve. You've got your sine function, you've got your tangent function, and you've got y equals x. Close to the origin, those curves almost match up. So that's why we can say they're approximately the same when we're close to x equals 0, or theta equals 0, I should say. Any other questions?
Just had a question about y, like the little y.
The vertical height here?
So that, yeah, so that would be the distance from the central maximum to whatever point we're interested in, right? Either a dark one or a light point?
Right. In some problems, you can also see delta y. Delta y just means the distance from bright spot to bright spot. Regardless of the center, just from a bright spot to the next bright spot would be called delta y. So you might see that notation.
Okay.
But y itself is supposed to represent the distance from the center, which we're calling y equals 0, up to whatever bright spot or dark spot we care about. Any other questions on that?
Yeah, I just had one question. So in like the previous drawing that you drew on the right side, I think you erased it, but it was the theta going from the slit to whatever point at the top, but then this one is from like the middle to like the top. So does theta like specify whether it's from the middle, or does that just say like any elevation point?
It's actually going to be about the same because we're assuming that the slits are very close together. If we actually look at a situation where the slits are close together like they should be, so like here and here, if we draw out this line of sight and this line of sight and measure horizontal to this angle and horizontal to this angle, those angles are going to be almost the same anyway.
Oh, okay. That makes sense. Thank you.
And again, this hinges on the geometry and the assumption that these slits are very close together, that the distance little d is very, very small compared to the distance between the walls. Any other questions? All right, I've got to get to a meeting. Feel free to email me if you have any other questions, and I'll be in office hours tomorrow if you need me. Otherwise, have a good weekend, and I'll see you next time.
Thank you.
Thanks.
You're welcome.